Welcome to lecture number 2. All right, we've been talking about hypothesis testing, and so far all we've been talking about with hypothesis testing is hypothesis testing about the mean of a population. Well, sometimes you're interested not in the mean of the population, but sometimes your population is divided into two categories, a category of success and a category of failure. Maybe your population is a population of parts. Most of those parts, hopefully, are parts that work, and a certain percentage of those, or proportion of that population of parts does not work. Perhaps your population is a population of the United States that is going to be voting on an election in coming weeks, and we have a proportion of the population that is going to vote for a particular candidate or is not going to vote for a particular candidate. So that's what we're going to be talking about in this lecture. So I'm going to use the letter P as my symbol for the true proportion of a population that is going to vote or that meets my criteria. So P is the proportion of my population that matches a criteria. So what I'm going to do, I want to find out what that proportion is. I don't know what that proportion is, so I'm going to take a random sample. And in that random sample, the number of my random variable x is going to be the number of observations in a random sample of, let's say, size n that meets the criteria. So now I can say, and I can use as a point estimator for my prediction of what P is, that P hat is equal to x over n. So P hat is my point estimator of P. Now, something about P and P hat. Remember, I've set up a situation where somebody, a member of this population, either fits into this category or does not. It's a success-failure situation. And if the example is, for example, the election, the fact that you're voting for a particular candidate has no bearing on whether you're voting for a particular candidate. So the individual members of the population, whether they fit into the criteria or not, is independent of one another. So I have independence, I have a true-false situation, I have exactly the situation where we use the binomial distribution. Also, I'm probably going to pick a fairly large sample size for my study. So n is going to be fairly large. I can probably say that NP is probably going to be greater than 5, and that n times 1 minus p, 1 minus p is probably going to be greater than 5. So not only do I have a binomial distribution, but I have a binomial distribution that I can approximate with a normal distribution. So using the same nomenclature that we found before for approximating the binomial distribution with a normal distribution, I have z is equal to x minus np over the square root of np times 1 minus p. And this will have an approximate normal distribution. So if I wanted to do a p-test, let's say I found my my p hat, and I wanted to do a p-test to see how likely it is that a particular hypothesis of what I supposed might be the true proportion p, I can do a p-test just like I did with the mean. So if I could set that up, I might set that up by saying that h naught is that my proportion is equal to some value p naught, and that my alternative hypothesis, I'm sorry, that it is equal to, that p is not equal to some proportion p naught. I have the same basic setup where I have 0, 1/2 of alpha. That area is 1/2 of alpha. And I can use all the same architecture that we used for the testing of the mean with testing of a proportion. And we'll do some examples of this in the coming days, in the lectures that weren't messed up. Now, the rest of this section basically goes through the same order, the same logic as when we came up with the proportions for the for all of the mechanics for the mean. I'm not going to go through all of that step by step. You'll recall that one of the things we were looking at was when you had a when you had a given alpha and a given beta, and you wanted to know what sample to take in order to detect whether or not a true proportion, which was differentiated from the hypothesized mean, there was a formula that we came up with for that sample size. We have the same thing for proportion. The derivation is almost the same, so I'm not going to go through it. I'm just going to write down the final result, which is that n is equal to ZA P naught 1 minus P plus Z beta, the square root of P 1 minus P all over P minus P naught squared. And you'll see that that is similar to what we found before. I should also say that if I wanted to test this hypothesis with a p-test, I find the p-test, the p-value, the exact same way I find the p-value for the mean. My p-values are exactly the same. I do want to clarify, we've got a lot of p's floating around. We've got a p for proportion, and we've got p-value. This here is the p-value. So if I wanted to find how far away, how unlikely it is that I would get a particular p hat if my hypothesized p naught were true, that's this p right here, the p-value. And as I could say, I just put this up here. It's exactly the same formulas for the p-values that we came up with when we were talking about the p-values for the mean. All right? This is the end of lecture 2. I've got one more of these lectures to go. It should be fairly short to come up with the confidence interval for a proportion. I'll see you in a few minutes.